Thanks for having me here. Thanks for braving the rain and so on. Just to begin with, just to introduce myself a little bit, I never actually planned to be a biologist at all. I was originally trained in art, actually, and then also mathematics. And after sort of a convoluted career path, ended up as a biologist. And for me, it's ended up being a perfect career because, as you all know, being in this area, animals are just so incredibly beautiful. And you can use things like mathematics, biology, and physics to help understand the way they look that they do. So it's been wonderful for me, and because of the art background, I've always been very interested in how things look and how they interact with light and how their vision works. So I'm particularly interested in color, bioluminescence, camouflage, signaling, things of that sort. Today I'd like to talk a little bit about what goes on in the open ocean in the waters around Saba. So most of you, when you dive, you're somewhere near the coast, you're on a coral reef, maybe you're in seagrass, kelp, things of that sort. And the waters I'm talking about are beyond that. They're the areas of the open ocean which you can usually only reach by larger ships, though they're relatively close here because things get deep pretty quickly. This habitat is enormous. It's actually about 99.5% of the Earth's livable space. If an alien were to come to the Earth and stick down his or her hand into the world and pull out an animal, they would pull out an animal from the middle of the ocean. Despite that, it's just about the least understood habitat you can imagine. And the reason for this is that it's a very, very difficult habitat to study. Water lets us see for some distance, but not much farther than that. There's the pressure, there's all the other things that make it very difficult to get down in there. And so until recently, most of what we've known about the ocean has involved using nets, where you basically scoop a net through the water and pull out and see what you get. If you could imagine what it would be like, imagine you're all sitting there, you're enjoying lasagna, eating and so on, and then a giant bulldozer were to push straight through that wall and scoop all of you up in a bucket of the bulldozer, and then just start pushing you, 10, 20 miles, I guess we'd have to go out on the ocean here, and just keep pushing, 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 and while you're in this bulldozer thing, you're clawing and screaming and yelling and cannibalizing each other and so on, and then somebody were to dump you in a bucket, and you're half dismembered at that point, and then just start sorting through, trying to figure out who was sitting next to who wanted to do what they were eating dinner, and so on. You get very little from it. So a friend of mine once said that using nets to understand oceanography is a lot like dragging a grappling hook over London and then trying to understand personality of English people. It just doesn't work very well. So we use other techniques, but even those aren't perfect. One of the techniques we use is called blue water diving. It's basically scuba diving, except you're doing it over extraordinarily deep water. The waters we're over are anywhere between 3,000 and 6,000 meters deep. The visibility is 100 meters or more. There's absolutely nothing in any direction to look at. There's no reefs or anything. You're just looking at water and the animals that live in it. This is an experience I'm going to try to create a facsimile of on Thursday's dive, for those of you who want to come, to sort of show you what actually lives in the water column. It's an extraordinary form of diving, and in some ways very disorienting, and it gives you an idea of what it's actually like to be one of these little animals living out there. Unfortunately, you can only go so deep, and so we use submersibles to go deeper. This is the Johnson Sea&Learn submersible that goes down to depths of about 1,000 meters.
Thursday? Thursday?
Next Friday, actually. Yeah, I brought it in my check bags. It's sort of fun. Very cool toy. But the problem with everything, even with these neat, toys and different ways of going down and observing, we never really get to see what the animals would act like if we weren't there, which is something we can relatively easily do on land. Suppose you wanted to know how beavers behave. You could set up a little camera in a beaver lodge, or you could hide in a certain place. You could watch them behave and learn how they work. This simply does not work in the open ocean because, for one, there's absolutely nothing to hide behind, and animals are exquisitely sensitive to everything going on around them. So in the case of the submersible, this thing's about the size of a school bus, and it's got about 20 lights on it, 20 different propellers, and so it's very much imagining like a school bus full of screaming kids with all of its lights on at night, coming up upon like some poor little bunny sitting on the side of the road, and then your bunnies are sort of looking up, and then everybody goes, just act naturally, do what you normally do. In addition to that is the fact that these lights are bright enough that they can end up at least temporarily blinding the animals that they see. So really all we're really observing when we go down in these submersibles is basically stark terror. And it's very difficult to figure out what's really going on. So we do what I like to call forensic biology, where we take animals from the deep and we're actually able to bring them up onto ships and study them. And then from what we know about what we can study on the ship and from what we know about the environment, we can then deduce what's actually going on. There's an example of it here. You find a funny little animal which has really long teeth, happens to be next to some wood that was just chewed on, and you think, and then you come to the conclusion that this little animal with the long teeth actually chews on wood. I mean, in the ideal world, you'd actually like to see the animal actually doing the chewing, but if this animal happens to be at the bottom of the ocean, you're not going to get that chance. And this is basically where deep sea biology sits at the moment. So the particular problem I'd like to talk to you about today is why do animals in the open ocean look the way they do? Those of you who dove on coral reefs, you know that animals come in a riot of colors and patterns. Every single color in the rainbow, the stripe pattern, I mean, everything you can imagine. And the functions that those colors serve are all over the map. Some are hiding, some are signaling, some are identifying themselves as members of certain species, some are doing all at the same time. In the ocean, though, things are a lot simpler. It doesn't really matter where you are in the ocean, you see this exact same pattern once you're away from the coast. At the very top, you have animals that are intensely blue over their entire bodies. And then as you go a little farther down, you have animals that look sort of like tuna. They're dark blue on the surface, sort of lighter blue on the side, and then become silvery and white on the bottom. But then you also get a lot of animals that are completely invisible. They're essentially transparent. Going farther down, you have more and more of these transparent animals, but then the opaque parts that they have remaining turn red. And then you go a little deeper than that, and by this point you're about 800 meters underwater. Animals are either entirely deep red, or they're deep black. And then when you hit the bottom, they become sort of much paler in coloration. They're tan to sort of a salmon coloration. And you see this wherever you go. It doesn't matter if you're in the Atlantic, Pacific, Indian Ocean, Antarctica, so on and so on. All that matters is sort of how deep you are. And there's really only one reason behind all this coloration, and that is predation. As far as I know, this is Photoshop. Nobody's ever actually told me one way or the other, but my guess is it is Photoshop. Predation in the open ocean, meaning that you're away from the coast, is intense. Predation everywhere can be intense if you're some poor small little animal, but it's particularly bad in the ocean for several reasons. One is three-dimensional. You can be attacked from every direction, including from below. The other is that there's nothing to hide behind. If somebody were to come in this room, some large predator, ant shark, whatever, and start running around, you guys could duck under tables, you could go in the closet, you could run in the bathroom, and so on. None of that is available to these animals. There's absolutely nowhere to hide. And in general, the predators move a lot faster than the prey. And so unless the prey animal is defended by some sort of chemical or poison, the way some jellyfish are, once it's seen, it's all over. There's nothing it can do. And those of you who've seen movies of predation in the open ocean, there's some really nice ones on Blue Planet. They show a group of large predators coming in and eating every single animal that's there, even if it's in the thousands. So you really need to be able to hide well. And you need to blend into a background that is exceptionally simple, which makes it also more complicated to hide. Because if you're on some very complicated background, you can blend it pretty easily. But if the background is incredibly simple, just a big sheet of blue, it's very difficult to hide. And so animals in the open ocean have evolved a whole number of amazing tricks to hide, which is what I want to talk to you about today. The four main groups are transparency, cryptic coloration, and cryptic coloration is what you normally think of as being patterned to camouflage yourself, like camouflage pants or so on. Mirrors, which we'll talk more about in a moment, and counter-illumination, where you actually hide yourself using light. So starting out with transparency, some of you may be old enough to remember Wonder Woman, the show, and she had this transparent airplane. I guess I was about 5 when the show came on, and what I was most fascinated by in the whole show was actually a transparent airplane. And there are a host of animals in the open ocean that essentially use transparency to hide. And they're able to match the background because you can see the background directly through them. And some of them you know pretty well, especially if you've been out scuba diving, but some will be a lot less familiar to. I'm going to do sort of a quick tour of some of these animals. The ones you probably know the best are jellyfish. Your standard jellyfish. There are a number of different kinds of these. This particular one's called Cunina. It's a deep sea jellyfish. It's about the size of your fist. And actually, all these animals I'm showing are not microscopic or small by any stretch. Most of them are at least the size of your thumb, and some are about 80 meters long. So not small animals at all. Talking about slightly weirder animals, this is a siphonophore. The closest animal that you might have seen that is related to this is a Portuguese man of war. These guys, this particular one gets to be about 30 centimeters long. And it's really neat because it's entirely transparent, but then there's all those little white spots in there look like small fish or copepods, basically like a meal. And they stretch them out on the end of poisonous tentacles. And so you don't see the main animal, but you see a cloud of what looks like something good to eat. And then predators come in thinking they're going to get those little copepods or little fish, and they get sucked into this big, very toxic animal that kills them. Those are some of the ones that get to be about 70, 80 meters long in the deep sea. Enormous animals. You also have the comb jellies, which some of you have seen off of these shores. There are a tremendous number of them. They get to be about the size of about a fist or two. This one's called Bathysauroid. And then you get to animals that have relatives that you know, but you've never seen what they look like in the open ocean as swimmers. These are all mollusks. These are all snakes. The one in the upper left is a nudibranch. Nudibranchs, actually, I think Gustav Pauli is going to talk about them soon. But nudibranchs are these fat little slug-like animals that live in the ocean, sort of go along like that. The ones that actually live in the water column are transparent. They're flattened like fish, have a fish tail, and swim along just like fish. And they're also bioluminescent. In the upper right is an animal, it's called a heteropod. It's a kind of a snail that's adapted itself to swim through the water column. It's got a tiny little shell that doesn't weigh that much anymore, and its foot is turned into a little fin to help it swim. The one on the lower left is called a pteropod. Its official name is Corolla. And these guys are especially neat. They get to be about like the size of your hand, but they spin out a mucus web that's about 2 meters across that they hang from, and then they collect food in this mucus web like a big butterfly net all day, and then when it's full, they suck the whole mucus web and all the food into their mouth, sort out the food, and then spit the mucus back out. So it's basically like eating your snot all day. It's pretty amazing. And then you get a lot of transparent squid and octopus of all different kinds, and these things just look like living crystal, and they're just amazing. Then you also get transparent worms of all different kinds. One of my favorites is the one up on the left here. It's called an alceopid worm, and it's actually the third evolution of a big camera eye, the same kind of eyes that we have. So these guys are actually predators with really good vision. The one on the bottom is called Tomopterus. These things get to be about 60 centimeters long, pretty big, so it looks like a big 60 centimeter transparent thing just moving through the water. The one on the upper right is probably the most abundant animal on the planet that nobody's ever knows about. It's called Poibius, and it lives at depths of about 4,000 to 6,000 meters down, and the whole ocean is just absolutely full of these things swimming around doing their weird little Poibius thing.
Why is the one in the upper left your favorite? I mean, that's just curious.
Why do I like that particular one? Because I just like them because those eyes are so weird, and they can see UV light, and there's no UV light at depth, so they're a total mystery. Why have an animal that can see something that isn't actually there, and we're still trying to figure out what it is that we're looking at? And they're great little predators, and so it's like this sort of transparent predator with these giant eyeballs. It would be like each of your eyeballs was the size of your head, compared. So they just kind of crack me up. They're funny. These are all transparent crustaceans. The one on the upper left is called Cystosoma. It's a member of a group called the Hyperiid amphipods. And these are parasites on jellyfish. The bigger the animal, the bigger the jellyfish it parasitizes. The one on the upper right is also a Hyperiid amphipod. This one's called Phronema. And what it's carrying on the left of it there is an animal that it has gutted. The animal used to be something called a salp, and it came and then it scooped out all the innards, and then it secretes a chemical that changes the shell to make it sort of hard, rubberizes it, and then it turns it into a nesting area for its babies, and then when the babies are born, the babies live in there and it pushes them around like a baby bug. So not surprisingly, this little critter there on the upper right was actually the inspiration for Alien, the movie. The original Alien was actually going to be transparent, but they couldn't afford the CGI budget, so they made it black. Sort of history was made after that. So it's a really creepy pretty animal, but it's only about 1 inch long, so you never have to worry about it. Then you get like larvae of spiny lobster. Those are the ones in the lower left there. Just these extraordinarily transparent critters. And then you get a few freshwater ones, like the one on the lower right there is called Lepidora. It's got one giant eye in the middle of its head that sort of fills it up with this big cyclops eye. Then you get weird critters that you just have no relative anywhere close to land. This is called an arrowworm or a pedanath. And there are tremendous numbers of these things in like the top sort of 10 meters of the ocean, just everywhere. Then you get the animals that are actually most closely related to us. These are the groups that are chordates or urochordates. On the upper left, you have something called a salp. That was the poor animal that got gutted by the alien inspiration. Upper right, you have actually our closest relative that's not a vertebrate. It's called a larvacean. You can see it actually has a little tail. The idea is it's sort of one of the original evolutions of our backbone and so on. The one on the lower right is called a doliola. These form chains that are about 10 to 15 meters long. We've been on dives out there where we're surrounded by dozens of these things, each 10 to 15 meters long, just snaking around us. They're just amazing critters. And then you also have transparent fish, usually larval forms. And so they'll get to be, maybe at most like 8, 9 centimeters long or so, but they're just very, very clear, and some freshwater ones too. So those are all glamour shots. You take pictures over and over, you have a flash on the side, a black background, and you take 100 pictures, you say the one that worked out the best, you say that was the picture you took. And they make the animals very obvious, but this is not the way they look when you're actually in the water. This is what you actually see when you're scuba diving. You're sort of looking around, there's actually animals in here. There's one right in the middle, there it is, and it's gone. The only thing that's giving it away at all is it's sort of a suspiciously spherical object. And this is one of the things we do when we're scuba diving looking for them, is we look for suspiciously spherical objects, because those probably aren't trash. Well, we look for pairs of suspiciously spherical objects, because those are usually eyes. The actual animal you often can't see. One of the ways that makes it a little easier is we look at a black background, and the easiest black background are other people's dive suits. And so we spend a lot of time all diving just staring at each other in our dive suits. And usually if there's a new person diving who doesn't know any of this, we all do it to that person, so they kind of wait out after a while. I don't know why you're all staring at them. But then when you get the black background, you can actually see that the water is just filled with all these different transparent animals. Most of these are such good camouflage that they can be right in front of your face. You see it for a moment, you reach down and get a little jar to collect it, you stick your head back up, and you know it's right there in front of you, but you can't see it. So very good form of camouflage. So how to do it? And I can only get into this a little bit. I give entire talks on this, but I just want to go through a lot of different things, so I'll just give you some of the highlights. One of the ways to do it is to be very thin. The animal on the left is that spiny lobster larva again. This thing's, about as thick as a few sheets of paper, and it manages to keep all of its organs and everything still working even with that. And the advantage is just about anything, if you make it thin enough, will start to become clear, even metal. So they're quite clear. And then the thing on the right is a leptocephalus larva of an eel. These are all over the oceans around here, actually particularly around this area. And they get to be about 30 centimeters long. And again, without any sort of glamour lighting and flash, they're basically invisible. And then a number of animals don't actually look flat, but the real animal, the part with the actual cells, is a very thin layer painted around a larger transparent blob. So many jellyfish have a pretty much non-living part in the middle that's the actual jelly, and then the animal part with the cells is very, very thin all around it. If you were to somehow peel that off and put it all together, you would actually see the animal because it would then be thick enough. But when you spread it all thin, then they become transparent and invisible. So in a way, it's sort of like you're painting an animal around something. One of the things that transparent animals have to worry about are their eyes. So to see, your eyes have to absorb light, which means they're going to cast a shadow. There are a couple of ways around this. What you're looking at on the left, upper left, is that cystosoma again, that large hyperion amphipod, and the flashes at it just right so that you can see the retina. That whole thing in the front that you think is head is actually two gigantic eyes. Pretty much the entire head is two eyes. And that little bit of orange coloration is the retina. They smear the retina with a very, very thin layer behind each of the little facets of the compound eyes. So while it casts a big shadow, the shadow is very faint, so you almost never see it unless you hit it just right with a flash. The one on the upper right does it differently. This is the head of that phronema, and all the stuff on the top is all the lenses of its compound eye. It has many, they're very large eyes that it uses for finding its prey. And then you see near the bottom, you see 4 sort of weird misshapen blobs. Those are actually its retinas, the actual cells that see where the rods and cones would be. And you can see they're all small and smushed up. You can't really figure out how the light's actually supposed to focus onto them. But they don't worry about that because they actually wire up their lenses to the cells of their retina using fiber optic cables. So their entire head is essentially a telecommunications network with fiber optic cables inside it. Whenever we tell this to like telecom engineers, they just start drooling because they make these things way better than the telecom people can. They're extremely thin and they taper down and they're actually more or less perfect for the conduits for light. So these eyes work on a totally different principle. The other thing, which I'll get to more later, is counter-illumination. This squid that you're looking at on the lower left, you notice a bunch of circles on either side. Those are right below the eyes. And what those are, they're photophores that produce light. E. Witter came last year and talked about bioluminescence, and this is one of the things you can do with bioluminescence, is even though the eyes would normally create a shadow, the light coming through from above, these animals have lights that exactly match the color, brightness, and angular distribution of the light from above. And they do it continuously, up and down. So every time a cloud passes over the sun, they change the amount of light they put out. And so they're able to make the silhouette just go away, sort of do the trick of the light. The other thing you have to worry about if you're a transparent animal is what do you do with your food? It turns out that even if you eat transparent animals, they're no longer transparent when they're being chewed up and digested. They start to look pretty opaque, and a lot of other animals are opaque. The other problem is that many animals in the open ocean are bioluminescent, probably 80 to 90% of them. And they'll start glowing like mad as they're being chewed up and digested. And so once you eat something, if you're transparent, all of a sudden you start glowing like a beacon to everybody else. And so you need a gut, you need a stomach that's opaque, but you don't want it to show up. And so what they do, and a bunch of different ones do this, you can sort of see it right around this corner here, they have a needle-shaped gut. They have a gut that's like a long, thin rod, and they have muscles all around this gut that keep it vertical no matter which way the animal is tilted. So the animal goes like this, or whatever. There's a gimbling system with muscles that keeps it always vertical, so that animals that are looking up from below only see a little dot, because the needle head arm looks like a dot. So what about the animals looking from the sides? What they see is not much at all because it cloaks the whole needle with mirrors. They have these special biological mirrors that I'll talk about more in a moment that basically make it invisible from those directions too. And what a few other animals do, including the one on the lower right, is they get rid of all the messy parts of eating and they just suction feed. Meaning that what they do is they'll go up to an animal, they'll kill it, and then they'll suck all the juices out of it. And the juices tend to be pretty clear, and then they feast off the juices so they don't have to worry about being given away. But then what do you do with everything else? The rest of your body. Let's say you're flat, let's say you've taken care of your eyes, you've taken care of your stomach. What about the big part of your body? When I first started looking at this, people would say, well, transparent animals are transparent because they don't absorb any light, because they don't have pigments, they don't have skin color. I said, well, have you ever met an albino? They're like, well, yeah. I was like, was he invisible? I'm like, well, no. And that's because there's more going on. The other thing you have to worry about if you want to be invisible is not just absorbing light, you have to worry about scattering it. And scattering happens whenever tissue is complicated. Whenever the density of tissue changes over and over and over as you move through it, or whether any substance does that. And whenever that happens, every time it moves from one type of thing to another, absorbing much light, it's completely opaque. You can't read a book through an albino. Other substances that are like this are milk. Milk is actually a whole bunch of tiny little fat droplets floating around in liquid. Both the fat droplets and the liquid are clear. But because the fat and the liquid are different, the light bounces around a whole lot and doesn't make it through. The same is true for snow. It's a mixture of ice, which is clear, and air, which is also clear. But because they're different, the light bounces around and doesn't get through. And the same is also true of clouds. You have tiny little water droplets or tiny little ice that, again, makes the light bounce around and the light doesn't make it through. So one of the things we study in my lab, and I'd be happy to talk to you about more, after I finish it, because it gets really munchy crunchy, is how animals minimize scattering light while still maintaining enough complexity in their tissue to survive. And it turns out to be a really, really challenging problem because it's very hard to make yourself simple enough to be clear and still complicated enough to live. But there are animals that are just masters of this, and I wanted to show you this one here. It's called Hippopodius, which means horsefoot. It's another siphonophore, and on the left, you see that it's totally clear. This is what it normally looks like. On the right, it's opaque. And the difference is that the one on the right was touched about 2 seconds before. So this animal, normally clear, you touch it, and it becomes opaque. And then after about a couple of minutes, it becomes clear again. And if you touch it again, it becomes opaque. And there's a whole number of different animals like this in the ocean that can basically decloak. We have no idea why they do it, we just know that they do it on purpose. They just have this sort of ability to be invisible and then all of a sudden appear out of nowhere if somebody bothers them, which is one of those mysteries. Another thing, which I'll only just touch on very lightly, is that, so some of you at least have Polaroid sunglasses, right? Some of you. And you know what they're really good for is like looking through the water. Like if you go fishing, you're able to look through the top surface of the water. It turns out that many of the animals in the ocean can do this without actually having any little glasses on. They have the ability to see the polarization of light. And if you can do that, you can actually break this camouflage. There are animals looking at them at the top. This is what they normally look like, pretty hard to see. But then if you have Polaroid glasses on, like if you go scuba diving with them or so on, this is what they can actually look like. The exact same animals also light up like Christmas trees. So one of the things we like to look at in the lab is how animals hide, but then also how animals evolve new visual capabilities to break that camouflage. Sort of a continual evolutionary launch of this. So I wanted to switch now from transparency to coloration. And you know, coloration is at least the one form of camouflage that most of you have seen in one form or another. You know, it's all over this island if you look at all the different frogs and so on and so on. The coloration of the ocean is interesting because you also have to worry about the color of the light. On land, you know, light's generally white, but in the ocean it's extremely blue. So an animal that if you pull it out of the water that looks extremely colorful, if you put it in the water with that light, can actually hide really well. And a nice example of it is mahi-mahi. You pull it out of the water, you know, it's really wonderfully golden and blue and all these different colors. But if you put it in the water, it hides extraordinarily well. I love this photo because it shows how you're oriented in the water matters. So most of these mahi-mahi are tilted and the sun's pretty low, so they stick out. But there's one that's swimming vertically right there. There's actually two. You can see that when they're swimming vertically in the water, the combination of that yellow-blue body and the blue light on it end up creating a color that matches the background perfectly, as long as they're swimming vertically through the water. This is just sort of to show you how much things change when the lighting changes. Our brains are continually adjusting for this. It's something we call color constancy. So when we look at a white piece of paper all day, we think it's always white. But in reality, it's changing color depending on the light that's hitting it. So in daylight, it really is blue, and under tungsten light, like your old-style incandescent bulb, it really is that orange. It's just our brains are telling us, no, it's white, so then all of a sudden we see it as white. So you have to worry about that, especially when you think about the color of deep-sea animals. And I want to just quickly show you, one of the things we do is we try to work out, if an animal wants to hide in the ocean, exactly what color it should be, and does that match the colors of animals that we actually see. And this is the end result of a whole lot of math and physics and so on. But the end result is that you get animals near the surface that look very much like tuna. The red coloration as you go deeper is due to another thing that I'd be happy to talk about later in questions, but I'm going to skip over for now. But the ones near the surface, basically predicting what a tuna would look like. If you compare this to measurements of how tuna look, basic idea is that tuna are sort of like the ideal hiding animal. Other good ones are things like sailfish, marlin, any of those other ones with sort of the blue fading to white as you go to the side are just perfectly designed to hide. And so in those cases, they're all predators. And so it's actually the predators, in some cases, that are hiding more than the prey, which is interesting. This just shows what animals in more greener coastal waters would look like, and they end up matching different kinds of cod and other animals you see out there. So I wanted to switch gears again before coming back to color and talk about mirrors. So you've all seen sardines, You see herring, all these different shiny fish, and you may have always wondered, why are they shiny? It turns out they're shiny to hide. And an example of this is if you hold a mirror up in the ocean, if you hold it vertically, it basically looks invisible. And why is that? It's because the underwater light field is more or less symmetrical about the vertical axis. So if you have a line up and down, straight and down. So if you look in one direction, the light you see there, how bright it is, looks a lot like the light in the opposite direction. And so when you're looking at a vertical mirror, these little red lines here are little vertical mirrors attached to a fish's body. The spot you're actually looking at is up there on the upper left. But it looks just like the spot that you would see if you look directly through the animal. And so they're basically playing a mirror trick, and they're able to make it look like you're looking through them when what you're really looking at is something that's actually behind your head. It's a really amazing form of camouflage. This just sort of shows how much it depends on how they orient themselves. This fish here on the left is swimming vertically. It hides and matches the background really nicely. And then it twisted a little bit and all of a sudden caught some of the sunlight and then stuck out. This animal is only about less than a meter from the surface. This wouldn't be as big a problem as you go deeper. And it turns out that evolution has really taken advantage of this vertical mirror trick. And so what you're seeing here is sort of like a cross section through a fish, kind of like a salmon steak or so on. And the little red lines going all the way along the side here are the measured angles of those little mirrors. And what you see is that the mirrors actually are pretty close to vertical as you go around the fish. Even though the body of the fish is curved, basically within each scale, depending on where it is in the body, they've adjusted the mirror relative to the scale so the mirrors are vertical all the way around. And you see this in all the different mirrored fish out there, all the shiny fish, showing that they've evolved to become these perfect vertical mirrors in the ocean. This is to show that some of the mirrors are actually alive. One of the projects we work on, we look at squid and cuttlefish and octopus, and they also have mirrors in their skin that they used to hide, except these mirrors are alive. They're under neural control, and they can change what color of light they send back by changing the structure of their skins. And something we're looking into in a lot of detail right now. So I've talked about mirrors, and I've talked about coloring yourself. Both are pretty good, and both can be set up to perfectly hide you in a given situation. So, imagine you're like this frog here, you're sitting on this nice little background, and you can work it out so that you can perfectly match it. But suppose you come up on that frog, you surprise it, and it hops on the grass, and now it sticks out like a sore thumb. And so one of the questions we're interested in is what kind of camouflage is best at dealing with that? Things change in the water. Water becomes murky, time of day changes and so on. Is it better off to be a mirrored animal, or is it better off to be a colored animal? And the four things we looked at were the changing of the water, in other words, going from blue water to green water, which can happen in many places. The time of day, whether it's noon or sunset. The viewing direction, meaning that if the sun is over there, you look at the fish from this side, or you swim around the other side and look at it this way. And then finally, depth. If an animal's perfectly camouflaged, it's like 50 meters down, is it still perfectly camouflaged if you push it up towards the surface? And this, I'm not going to go into in any real details, just to sort of show you what we have to know to do these sorts of things. And the things we have to know is we have to know who's doing the looking. In this case, we picked a cod because we did this work actually on Cape Cod. You have to know how much light there is in the water of different colors. You have to know how clear the water is. You have to know what depth you're working at. And if you put all that together, you can figure out exactly how visible one animal is to another. And we actually use this to do things like design lures that are visible to one animal and invisible to another. One example is we design lures that can be visible to fish that somebody might want to catch, but not visible to sea turtles that we don't want biting on those particular hooks. So like, for longline fishing and so on, you don't want the turtles to be biting on the longline hooks. You can create things that swordfish can see, but that sea turtles can't. The end result of these is that it turns out it's much better to be a mirror. So these mirrored animals in the open ocean, all the different jacks and sardines and herrings and tarpons and so on, really not only have a good camouflage strategy, but they have one that works under almost all conditions. And that's just shown here. M basically means a mirror did better in this situation. C meant that being colored did better. So the end result is that mirrors are really good. And if you ever find yourself lost out in the open ocean, you might want to take a bunch of mirrors with you and hang them on different sides to keep things at bay. Another thing that came out of this was how much it really mattered which side you were looking at. And how one might explain why many predators tend to circle around schools of fish. In addition to sort of schooling them together, there's a big advantage. So imagine here you're looking at this fish. It's colored so that it perfectly matches the background. Now what I'm going to show you is going to look like the fish is rotating, but what really is happening is you're swimming around the fish to the other side. And in this case, the sun is fairly low on the horizon. So as you move around, more and more light is striking the fish, and the background is getting darker. And these are actually all real numbers, and so this is how it would actually look. By the time you get around to here, the fish that was beautifully camouflaged now sticks out like crazy. And so one great advantage that predators have when they're circling around in the ocean, especially when the sun is low, during sunrise, sunset, and so on, is that all of a sudden some of the animals that were completely hidden before will all of a sudden stick out like a sore thumb. Final thing that came out of this was that the whole idea of having a white belly as camouflage, from animals who look at you from below, doesn't work at all. There's so much light coming down from above, and so little coming up from below to bounce off it, that you actually can't tell if this person's wearing a white wetsuit, a pink wetsuit, a black wetsuit, or whatever. In fact, they'll all look black. And because this is where the most light is, looking up, this is also a direction that many deep sea fish like to look. These are just some different angler fish from the deep sea. These guys are actually looking up to look at their lures, but I like them so much because they're such creepy little ugly guys. I'll show them more of these on Friday. But in general, one of the reasons that deep sea fish look so creepy is one, they tend to have really, really huge teeth. But the other is that they have these sort of upward staring eyes. And they're doing that because that's where most of the light is, and also because it's very, very difficult to hide that big silhouette unless you're transparent. You can make it as white as possible, you can make it the most blazing or whatever, it's still going to stick out. So there's really only one good solution, which is counter-illumination, which I talked about before. Many of the animals in the open ocean, many of the shrimp, many of the fish, many of the squid, their entire bottoms that they face down towards these animals and looking up have just hundreds to thousands of tiny little photophores, tiny little light-emitting organs. And that, like I said before, they can match the color, the brightness, and the angular distribution of the light that is coming down all around them, and so they completely blend in with the background. How they can do this is really not known, because the interesting thing is they can't see their bioluminescence. Their eyes are generally looking forward or up, and they can't see their bellies at all. And so somehow, they can tell how much light is coming down from above, but they can't look down at their own belly to see if they're doing the right job to match it. And so this is another one of those big open questions in deep sea biology is how on earth are animals, seeing something that they can't see and doing it so well. The last story I wanted to talk about is connected to bioluminescence, but in a very different way. And that is what's going on with the coloration of animals in the deep sea, meaning animals that are sort of 600 meters and deeper. Like I mentioned, when you look at how animals hide in the upper column, the predictions you make for perfect hiding animals are actually found. Things like tuna and so on and so on. But when you look at the animals that are deeper down, you see many of them are just this really, really red coloration. They're either transparent, but the parts that are opaque are deep, deep red. And the question is, are they really actually trying to hide by being this red? Does that actually work? And so, first we tried to predict, how, much red do they really need to use to hide. The important thing to know is that the red isn't there to make them red. The red is there because what they really do is absorbing blue light. They're trying to make themselves blacker in the blue. They're not trying to make themselves red. And so they have a pigment that makes them really, really dark in the blue. And the question is, are they doing the right amount of this, or are they doing too much? And so again, the only thing I want you to take away from this is that the important range to worry about, this is the wavelength of light here, is this area between 400 and 500. This is where blue light is in the ocean. And this is the only light we find at depth. It's basically a very blue ocean down there. So that's the range you care about. You don't care what happens outside. And within that range, the prediction for how much light you should still reflect is somewhere between like 30 and 60%. You should be dark in that range, but you still should reflect about half the light that hits you if you want to blend in perfectly. And so we wanted to measure that. We use this submersible to go down. Like I mentioned, these things are about the size of a small school bus on the outside. They're actually really cramped on the inside. This particular submersible is divided into 2 compartments. The lucky people are in the front, that thing that look like the big bubble, and you get to look in all directions like a helicopter. If you're unlucky, you're in the back with the backup pilot. This thing's about the size of a double-wide coffin on the inside, just has 2 little portals to look out. And this guy's only there in case the people in the front die. If something happens, the submersible breaks, it ruptures, they implode, whatever, it's his job to reach up and pull one of those valves and then bring you back up to the surface. As long as nobody's dying in the front, he's usually either reading a book, which he's doing right now, or he's arguing with you about gun laws. For some reason, some pilots really have to think about gun laws. And like I said, you're in an area the size of a double-wide coffin, so you learn a lot of diplomacy. So you go down, we get the animals, and then this is just a schematic showing that we can actually measure their color, how much light is reflected from them, and at what colors they reflect light. And there's all kinds of wonderful little compact tools we can use now to make this a lot cheaper and easier than it used to be. And so you get a bunch of reflectances, how much light they reflect at different wavelengths. Again, what we care about is what's going on between 400 and 500, because that's what the blue light is. And the take-home message from this, with all these red lines are from different animals, you notice that they're very, very low in that range. And the prediction for hiding was that they should reflect about half the light, about 30, 50, 60%. You can see they're much, much lower than that. Some of these are only reflecting like well less than 1% of the light. They're basically black in the range that matters. In other words, they should stick out pretty badly if all they're trying to do is match the background light. If they're trying to do that, they're doing a terrible job. So what are they worried about? I mean, why use up all that pigment? They have to eat this pigment to get it into their bodies. It's very expensive, it's costly, and they're putting in so much that they're actually overshooting by a long shot. So why do it? It turns out that they have one other source of light to worry about, and that is animals with flashlights. A lot of different fish and a lot of different crustaceans that are predators have a flashlight built into their cheeks that aims directly forward and illuminates things around them. And because they're shining directly into the water, anything that reflects back is not water. It's something interesting that they might want to go look at. And if you've ever walked around at night with a flashlight and you shine it at a pane of glass, you'll notice that the light comes back at you. And that's because even transparent things can reflect light under that situation. So even the transparent animals are in trouble down here. And what they do, and what all the other animals do when they get down to the realm of where all these little flashlight fish are running around, is they make themselves as dark in that blue range as possible. They want to be just pitch black. They just suck up all that light, so none of that light bounces back to the animal with the flashlight, and they won't come investigate you. This is just sort of show how well that works. What you're looking at, the little red histogram shows where the minimum reflectance is, basically where they're trying to be as dark as possible. And then comparing that to where the light of the bioluminescence is the brightest, and where the vision of the predators is the best, and where the water is clear. So you can see that they all line up. Basically, there's sort of a zone of death in this sort of blue coloration, where if you reflect any light there are animals that can produce it, there are animals that can see it very well, and the water transmits it the best. And so, you're in real trouble, so they try to make themselves as dark as possible. However, there are animals with red flashlights. This is sort of the last thing I wanted to end with. There are a small number of animals that, in addition to their blue flashlight, have a little red flashlight right next to it. And so these animals can see all the red animals extremely well. Even better, almost nobody else can see them, because almost no animals in the deep sea can see red. So these guys basically have sniper scopes. They have infrared goggles. Nobody else can see them. They can go around and pick out all the red animals, eat them as much as they want. The neatest thing is that the way that they can see this light that's so red is they actually eat chlorophyll from algae that have floated down from the surface waters, and they incorporate part of that chlorophyll in their retina. And that allows them to see red better than other animals can in a normal situation. So this animal is basically using, the chlorophyll from dead plants to prey on animals in the deep sea, which I think is just one of these wonderful kind of circle of life things. And with that, I just wanted to stop and take questions. I know you must have at least a couple questions. Yeah?
How do you take the photos of all the transparent detection?
Yeah, well, so we do some photos actually in the water, and that's extremely difficult to do because, you're floating around and the animal's floating, it can be a real drag. Most of the animals we bring up on the ship and then we take pictures of them there with flashes and so on. Like I said, most of the pictures involve taking about 100 bad pictures, and we never show anybody the bad pictures, so it looks like we're really good photographers. But all you have to do is get lucky about once every 100 times when you post that one. Yeah?
When you plan your deep water dive like that, how do you figure out a plan to dive in when you're over deep water, just maybe 3 meters?
Oh, so when we do the blue water diving?
Yeah, how do you?
Yeah, it turns out, so, what we're going to try on Thursday isn't going to be quite the real thing because we're not really out in the middle of the ocean. And we're not, near any very deep water. But in the cases where we do it, out in the ocean, it has some risks. The biggest risk is, there's nothing around us. We're usually several hundred kilometers from land. And we take we have a ship that's, usually about 80 to 100 meters long. And then that ship launches a small boat, and we go out usually with about 5 divers. And then we tether a float to the small boat, and then we have about a 50-meter line that goes down from that. And then we have a system called a trapeze. It's a set of lines that attaches to a central meeting point that we take down to the depth we're going to dive. And everybody's hooked into those by a pulley system. And so you can swim away about 10 meters away, and then this weight will go up. And then as you move back towards the weight, will go down. And then there's one safety diver in the middle that keeps all the lines from getting tangled up. Before they did this, there were a number of big problems. One, it was very easy to blow your depth profile. The water is exceedingly clear, and so you don't actually notice when you're sitting there with a little jar trying to find a little animal or so on, that you've actually dropped to very deep depths. Because the light won't even change so much. A lot of the normal cues you'll get, you won't get. And it was also very easy to drift away from the boat and then just never be seen again. So the safety diver is there to make sure that all the divers are accounted for, that they're safe, that they're not tangled up. It also looks out for sharks. Because one problem is, so on a reef, sharks are generally not a big problem. I mean, you're basically swimming around inside the refrigerator. There's food everywhere, why are they going to bother with you? In the open ocean, you run into sharks that maybe haven't eaten in a long time because the water can be fairly empty, for hundreds of miles. And so when they show up, they're far more interested than they are on reefs. So, I swim on reefs with sharks all the time, and they just swim by you. The open ocean, every time we've met a shark, it has been very interested and chased us out of the water. And a number of them are quite large. So you have a number of things you have to take care of. The main thing is just keeping track of all these different lines. And the lines also keep us from going up and down too much, because it gives us a reference point, because otherwise it gets very hard on the ears as you're continually chasing up and down, to catch different animals. But then, we're usually down about an hour, and we catch what we can catch, bring it up, and then go from there. It's a really neat kind of diving. It just involves a few extra safety procedures, but it's amazing how disorienting it is, because there's just no frame of reference at all. And so you'll actually watch scuba divers slowly turn upside down because they don't realize what's up anymore. And it's interesting. And you can't tell if what you're looking at is a really small animal close up or a really big one far away, which leads to problems with sharks because you can't tell if it's a really big one coming for you from a long way or if it's just a small one coming by. And you'll see people panic because they think it's some gigantic thing coming for you or something. It's an interesting experience. It gives people nightmares sometimes. Yeah.
When you're diving and you experience a little nip here or there, is it typically jellyfish or is it typically larvae or
It's different things. So sometimes it's jellyfish. It can also be parts of siphonophores. Like little tentacles will drag across you, give a little nip. There's also larval jellyfish that can get under your dive skin. Little thimble jellies and things of that sort that can do it. The other insects, and they don't bite like normally, like a normal insect when it bites, what it's really doing is injecting you and, pulling something out, like blood or whatever. They actually bite a piece out of you. They leave little holes. And in our experience, they're really fond of like areas where your skin are softer, like on your upper legs and so on. And we were in Belize for a month doing research this summer, and they were eating us alive. You just sit there and they would just chomp out pieces of you. So they're one of the other ones, and they'll just come in and big teeth and take a chunk.
Your teeth chomps or your teeth?
They bite deeply.
Oh, okay.
Well, I mean, deep enough that it's annoying and it hurts, and you see a little hole in you, and you're annoyed. Any other questions? All right, well, thanks. Appreciate it.